Welcome back to mechanics and control of robotic manipulator. So far what we have seen is actually like we started what is robot and we have come across so far what we call transformation matrix. This particular lecture we are going to talk about like a transformation matrix as a recap, and then we would be talking about individual rotation matrix. For example, if it is only rotated with x or y or z, how individual rotation matrix look like. And finally, we said in the last lecture itself we gave a break, say that this rotation matrix, if in real, so there is a three orientation how we can actually like put together as a composite rotation or compound rotation. So in the sense we would be introducing the compound rotation in this particular lecture, and we'll see how it goes one by one. So in that sense we can see like so the lecture how it goes. So we'll be recapping the transformation matrix. We'll not be seeing in detail, but we will be giving a brief. Then we will be taking the individual rotation matrix for example x-axis rotation, y-axis rotation and z-axis rotation. Then finally we will end up with what you call compound or composite rotation. So if that is the case, we can see like we will take the recap on you can say transformation matrix. So transformation matrix, we know like it is an operator which maps one frame to another frame in a compact matrix form. So this aids writing a compact equation as well as the conceptually clear than the other kind of equation. In the sense you can actually like make one body to another body, like that you can actually like stack each box would be represent as a transformation matrix. For example, this is transformation matrix of actually like 1 with respect to 0, this is 2 with respect to 1, and this is 3 with respect to 2. Like that you can actually like keep stacking, and inside this you would be having both you call rotational and positional information. This is what we did. So based on that, what we can see like the position of you can say q with respect to a, whereas the position of q with respect to b is given, and if we know the transformation matrix of b with respect to a, we can actually like get it the final end. So now we can see that the position vector here, the generalized position vector, we have increased to one dimension. So that is what we call it is actually like homogeneous you can say coordinate or homogeneous position vector. So here we have added the scaling factor. So in simplicity we take the scaling factor as 1, otherwise we can bring the original scale. So now you can see inside there is a rotation matrix and the position vector, where the rotation matrix we keep it as it is like 3 cross 3, and similarly the positional information between two frame also we keep it as a 3 cross 1 as a vector. So now this is what we are actually like writing as a transformation matrix. So now based on that, what you can see the transformation matrix is 4 cross 4, and this is what we are actually like saying that compact equation or compact form, and it is conceptually clear in the sense it would be having a homogeneous where the rotational and positional information is inbuilt. Okay. So I hope now you are clear. Even then we have actually like said when the perspective will come, if your projection or when you are looking the you can say position in a different view rather than orthographic you can say projection or orthographic view, so then this perspective vector will come. In reality most of the camera will have a perspection, so in the sense the perspective vector will come. Similarly for making sure that the scaling of the position, so we can actually like use the scaling factor. So for example you are taking a camera based positional information, so 1 pixel equal to how much we use that unit that you can actually like convert. In the sense this position vector still we can keep it in pixel, and the scaling factor will take in care of all those other conversions. So now we are clear on this. So we said that how this rotational information would be obtained in 3D case. So in the sense it would be having 3 orientational information, how we will get. So that is what we call compound rotation, but we will see how that can be obtained in this particular lecture. For going to that, so we will first of all talk about individual transformation, in the sense individual rotation matrix. For example, I have a frame A, so now there is a body which is actually like associated with A in such a way that initially the x axis is actually like coincide here, in the sense I bring the B frame where the xb unit vector and xa vector are actually like coincide. In the sense now I am actually like rotating with respect to this sum. So what happened this, so yb cap and zb cap would be actually like moved. So how much it moves, or actually like how we can get the rotation matrix, that is what the idea here. So now you can see like there is a phi angle rotated with respect to xb axis. So now you can see that A frame and B frame are actually like having only one, you can say, transformation, which is nothing but the rotational. So now we have to find this rotation matrix of B with respect to A, where the rotation happened with respect to x axis. So now you can look at it in that case. So what would be the projection? So you know this can be written as x B transformed to, you can say, A. So then YB unit vector actually like projected on A, and ZB unit vector projected on A. So this is what we did, and we have taken this is actually like simple direction cosine, or we call the dot product. So in the sense XB projected on XA, that would give 1 because both are actually like coincide. So then what happened? So the XB cannot be projected on YA or ZA because this is actually like coincide or parallel with XA. So in that sense that projection would be 0. So now what else you can see? The YB cap can be projected on XA, that would be 0 because that is in the other plane, YZ plane. But if I actually like project this, so if I actually like project this into here, so what that would be? That would be cos phi, and if I project on the ZA, that would be sin phi, right? So now that is what we are actually like writing, right? So similarly, you can actually like project this ZB unit vector on the YA frame. So that would be actually like cos 90 minus phi. So in the sense this is sin phi, but that would be opposite direction, and this would be cos phi. So in the sense what happens? So this is actually like, so minus sin phi, and this is cos phi, right? So like that we found the individual rotation matrix. So now what we have taken? So this is equal to R, you can say x of phi angle, right? So this is what we call individual rotation matrix. So now I hope this is what we have actually like written. So the rotation matrix of B with respect to A, where the rotation happened only with respect to x axis within a phi angle. So then we can write the rotation matrix in this form. This is what we have seen, right? So in the same continuation we will do it for the other axes. So now we can actually see that the A frame is given. Now the B frame has actually like come in such a way that YB axis actually like coincide with YA axis. So now in that case, if I actually like rotate with respect to this, so what happened? This would actually like move like this, right, or rotate like this. So now I call this is some angle. So for example, this is I call theta. So this theta angle I can actually like write RZ, so sorry, RY of theta. Can I write it? Yes. So for betterment or for better clarity, what we are actually like taking it. So we are taking it actually like YA actually like coming out of the screen. So that what happened? This ZX plane can be seen in the board. So now what happened? This is actually like coincide with YB cap, in the sense YB cap is coincide. Now you are rotating with respect to this. So what happened? This ZA moved to ZB cap. So this is what we call theta angle. So similarly, this is also rotated as a theta angle, right? So now the same way you can actually like project it, but what you can see, the XB, so this XB unit vector projected on, you can say, XA, so that would be cos phi, okay, in this case cos theta, and on YA cap that would be 0, and on the ZA cap that would be minus sin theta. So in the sense what it will come, so this one be actually like cos theta 0 minus sin theta is the first. Similarly Y, so YB projected on A frame, that would be 0 1 0 because it is actually like coincide. So now we take the ZB, so ZB projected on XA frame, that would be actually like sin theta. So ZB projected on YA cap, that would be 0, and the other way around it is actually projected on ZA frame, that would be cos theta. So now this is actually like what you can see, this is equivalent to the rotation matrix of Y with respect to or Y at an angle of theta, right? So now if I write, so RB with respect to A, where Y frame or Y axis is used for rotation, so this is what the matrix, right? So that is what we have written here. So you can see, so this is what we obtained. So this is another individual you call rotation matrix. So now we'll see the last one with respect to Z axis. So Z axis easily we can realize here, still we'll bring it back. So now we brought the B frame, where ZB is actually coincide with ZA. So now we are trying to rotate. So what happened, this XA would be rotated, that would be XA become XB cap, and this would be rotated, so that would be so YB cap, right. So this is actually like what we did here, right. So now the angle we call phi. So again you can see like it is not so very clear, so we'll take the same way. So we'll put ZA cap is actually like coming out of the screen, and we use the X and Y on the screen. So now in that sense, if I rotate, what happened, this would rotate and this also would rotate. So this rotate and a phi angle, this is also rotate and a phi angle. So now this is actually like YB cap, and this is actually like XB cap. So now we project XB cap to frame A. So that is what we are doing it. So now if we project XB cap on XA, so that would be cos phi, and the XB cap projected on Y, so that would be sin psi, okay, and XB cap projected on ZA frame, that would be 0. So similarly YB if you project, so that would be sin psi, but that would be the other side, so minus sin psi, and this would be cos psi, and this is 0, and ZB cap projected on X and Y, that would be 0, but in Z it would be 1. So this is equivalent to what, RZ of psi, right. So now if I rotate or if I use the rotation matrix of B with respect to A, so this is actually like this. So this is the final matrix. So now you can actually like see this is what we obtained. So this is going to be useful for the composite or compound rotation. So that's why we have done this. So let us actually like move to the compound rotation, what exactly we want to do it there. So what we are actually like doing it there. So the compound rotation, in the sense the order of rotation, because you have 3 axis rotation, right. So the order of rotation is very important. It actually like because it is actually like not supposed to be surprising, because if you take the order interchange, what happen, so your matrix multiplication will give different answer. That is what we have written. So multiplication of matrices is not commutative, right. So in the sense what happens, so if you have AB matrix, so this product is not same as this, right. So if you take the order is different, then the final answer would be completely different. So that's why we need to have some standard representation, so that we can actually like keep it that representation as a uniform, and anybody who uses this robotic system, so they can actually like say this is what I use, okay, they will understand, okay, this is the representation, this is the way we can actually like recall. So if that is the case, so what one can see, there are several common representation, we would be using 2 of them, and we would be addressing that here. So before that we will see what are the general, you can say the compound or composite rotation representations. So one would be we call global, you can say XYZ, in the sense a global roll pitch yaw, because roll pitch yaw usually we call it with respect to mobile frame, but here actually like what we call fixed angle, so you would be rotating with respect to the inertial frame. So inertial frame is rigidly fixed with respect to earth. So that's why we call it's a global XYZ fixed angle. So this was come from one of the, you can say, popular researcher what called Winkel. So the Winkel angle also some of the people used to call, especially if you go to European community, they call this as Winkel angle rather than global XY, or you can say global RPY angles, okay. So I hope now you are clear, there is one representation with respect to X axis rotation, Y axis rotation and Z axis rotation of, you can say, fixed frame, okay. So first we will rotate with respect to fixed frame X axis, then Y axis and Z axis. In the next lecture we will see that detail. So let us move the next you can say representation. I already said this globally we call roll pitch yaw or RPY angle, or some people call this is Winkel angle, okay. So let us actually like move what would be the other representation. So Euler gave there are 12 convention, there are 12 representation. So but we are actually like going to use one such, so we call ZYX Euler angle. Even there is other representation, but this is universally used especially in the mobile robot community and the manipulator community. So which is what we call ZYX Euler angle. So what that mean? So here actually like Euler angle all talk about the mobile frame rotation. Okay. So, mobile frame rotation were the consideration. So, in that case there are several configurations or conventions can come. In that one such convention we will take. So, first we will rotate z, then we will rotate y, and finally we rotate about x. So, this some people call actually like local RPY, but local RPY is a slightly different. We will see that in the next convention. Okay. So, this is actually like given by Garden or Bryant. So, even some people in European community they call this a Garden angle or Bryant angle. These are actually like same as Z, Y, X Euler angles. Okay. So, let us move to the next one. I said even some of the aerial robot community or aerial robotics community they use Z, Y, Z as a Euler angle. So, this is another popular, but this is mainly popular in aerial and space robots. And even the manipulator, some of the manipulator has a spherical joint. So, that cannot be done. So, what they do first z axis rotation, then you can say y axis rotation, again z axis rotation, that is what they use. So, in that sense you can actually like write as z y z Euler angle. So, then there is another representation which I said local RPY. So, where it is actually like x y z. So, but this is actually like on the mobile frame. So, that is why it is called roll pitch, yeah, but it is a local. This local RPY angle we call slightly different. The rotation about a local frame of x axis we call roll or bank. Similarly, rotation about local x axis, so we call roll and bank. Local y axis we call pitch and attitude. So, some people call attitude control. Attitude control means nothing but pitch control. Okay. So, please be clear. So, similarly, rotation about z axis of the local frame called yaw, some people call heading, some people call spin. Okay. Spin is actually like more commonly used for the roll, but the local frame when we you can say represent, the spin would be on the z axis. So, now you got some clarity. So, there are several representation. So, how we can actually like bring it these all into a picture. Similarly, you can see like several keyword we commonly use roll or bank. I think if you actually like follow some of the you can say aerial robot or you can say aerial vehicle based Hollywood movie and all say that I am banking, in the sense they are rolling. Okay. Similarly, people call actually like attitude control. So, this attitude control is not human attitude, this attitude in the sense the pitching. Okay. So, the pitching of the aerial vehicle or pitching of the you can say mobile robot all actually like very important, that is what we call pitch or attitude. Okay. So, then the final one is actually like very common, we usually call heading control or yaw control. Very rarely we use spin, but yaw or heading is actually like common. So, which would be about the local z axis rotation. Okay. So, now we will actually like go one additional slide, with that we will close this particular lecture. So, what that, so you can see like you have a several representation and several form. So, you have actually like rotated the axis with respect to frame, right. If you refer from the fixed frame, so you have certain format. If you are actually like moving or rotating with respect to moving frame or local frame, that is actually like set of another you can say regulations or some kind of set of procedures. What that? So, if you are actually like rotating with respect to fixed axis, then you have to pre-multiply that rotation matrix with respect to your position vector or your predefined rotations. Okay. However, if you are using the mobile frame, so what happen, you have to actually like rotate as post multiply in the sense. So, if you have a moving frame, then you have already one rotation. So, you have another, then this is actually like post multiply. So, this is with respect to moving frame, and whereas this, so this is R1 and R2, where this if you are using a fixed frame, so R1 and R2 is actually like pre-multiply. So, this is actually like something I will show you in one you can say slide, then you will get idea. So, this is what we call the comment. So, what comment is actually like if the mobile frame is to be rotated by an angle theta about kth unit vector of the fixed frame, then you pre-multiply with the rotation matrix, whereas if it is actually like rotated by an angle about its own you can say kth unit vector, then you post multiply with the rotation matrix. I hope you are actually like clear on that. So, for understanding that more you can say more clarity manner, so I brought two frames. Okay. So, just to give a clarity. So what clarity is actually like says that there is a frame A and B which are actually like put it here. So now if you look at it here, the rotation matrix of B with respect to A, I can simply write, you know, like XB can be projected on A frame. So in that case what happened, this would come 0 1 0. So YB frame, like YB axis projected on A frame, that would be you can see -1 because YB is opposite direction of XA, and this is 0 0, and ZB is actually like projected on the same, right. So this is the rotation matrix. Now I hope you are actually clear how it has come. So this is the rotation matrix. Now what I am taking is actually like there is a rotation about YA as a 90 degree, in the sense you are actually like rotating this 90 degree. So you have taken a B frame here and you are rotating. So what happened 90 degree if you rotate? So YB dash will come and ZB dash will come because you are rotated 90 degree like this, okay. So then this would be you can see XB dash, right. So now what we have done, we have taken the rotation with respect to, you can say, YA fixed, right. So we can actually like write that rotation matrix, okay. So this is the case. So if you write the rotation matrix with respect to A, so what that would be, XC is projected on YA, so in the sense 0 1 0, and YC is projected on ZA, so 0 0 1, and ZC projected on A frame which is coincide with the XA, so 1 0 0, right. So this is the final matrix which we obtained, but what we did, we have rotated with respect to YA. So what that would be, so this is what I can actually like write, so 90 degree. So what that, so that would be, you recall, so it is actually like written cos 90 degree, so 0, then this is minus sin 90 degree, right. That is why I derived the individual matrix. So 0 1 0, then this is sin 90 and 0 cos 90, right. So this is what we did it in the earlier you can say lecture. So I hope that you are actually like recalling. So or you can actually go back that particular slide. So now you substitute this, so this becomes 0, this become -1, this is 0 1 0, this is 1 0 0, sorry 1 0 0, right. So that is what I am actually like showing it here, right. So now, so if I actually like take these two matrices, if I actually like use the rule, since it is rotated with respect to the fixed frame, what I have to do, I have to pre-multiply this. So in the sense RBA YA rotated 90 degree multiply with RBA, whether it is giving this value or not. Fortunately you can see, so this is first and you multiply, you can see this 0. So this taken here, that is also 0, this, and the third row you can see it is actually like giving 1, right. So similarly here you take this and multiply 1 and this multiply with this 0 and 0 like third row, like that you can actually like take it. So this multiply with this 0, this multiply -1 and -1, so it become 1 and 0. So in the sense you can see the pre-multiplication is giving the right answer. However, the post multiplication can be do it or not. So for that what we are actually like taking it, we are taking it, so the RB, okay. So I am actually like taking RCB, so that I can see, so XC is actually like projected on B frame where it is coincide with XB, so 1 0 0. So where this YC is actually like projected on ZB, so in the sense 0 0 1, and where this ZC is projected on Y but opposite, so it is actually like 0 -1 0, right. So this is what we have written as RC with respect to B, in the sense rotation matrix of C with respect to B, but what rotation we did here with respect to XB. So in the sense you can recall what would be that, so that would be if I actually like write it correctly, so that would be 1 0 0, then cos you can say 90 degree minus sin 90 degree 0, okay. So sorry, this is 0, right, cos 90, this is, I will just erase it and write it, okay. So this we are writing, so 1 0 0, this is 0 0, this is cos 90 degree, this is minus sin 90 degree, okay. So then this is sin 90 and this is cos 90. So obviously this becomes 0 and this become -1 and +1. This is what the matrix. Now you need to get this, right? So already you have this. So what you can do, you can actually like multiply R B with respect to A and post multiply, right? That is what we have seen. So if you are actually like multiplying this, post multiply with this, so what you can see, 0 -1 0 multiply here, that becomes 0, and this, so you can see again that would be 0, this multiply with this, -1 -1, so it become 1. So similarly you can see this is coming. In the sense what one can actually like see, so this equal to, you can say, so R, so I will write it R B A and R C B, okay. So that is what we are actually like written as post multiplication and pre multiplication, okay. So I hope why we are doing pre multiplication and why we are doing post multiplication you would be clear. So if you have a fixed frame rotation, so then you can actually like pre multiply. If you are actually like rotating with the moving axis rotation, then you can actually like post multiply, okay. So with that I am closing this particular lecture. So the next lecture would be talking about more about this compound rotations. So I hope that would be clear in the next lecture. So right now you clear that, so why we are doing a fixed rotation, why we are actually like doing the moving rotation as post and pre multiplication, that you are clear, right? And why we are going with the compound rotation also you are must be clear, and in that two of the representation we are going to see, one is actually like Winkel angle, the other one is Cardan or Bryant angles. So with that, see you then, take care.